Okay, we're going to start from the very beginning and kind of give you guys a demo as to how you would actually set up your Sedona network. So from any Niagara-AX workbench version 3.6 or greater, you simply connect to a Jace. And what we're going to do, we have a Jace in our office that's running a Sedona demo, and we're going to start from setting up the network initially. So we'll go ahead and open up the station that's running on the Jace. Now, once you have this done, the first step is to run Sedona Installer and select the Sedona Framework TXS zip file that should be downloaded from our website or from Niagara Central and installed on your machine. So basically, open Sedona Installer, point to the appropriate folder in your Niagara directory, and you can see here we're running Sedona Framework TXS 1126.5. So you would select it, hit open, and then follow the on-screen prompts to complete the install. Now I'm going to cancel that because I already have the Sedona Framework installed on my machine, and I do not want the directories to be set up again because I have all of the appropriate kits and manifest. Once that takes place, you'll see in the left side of the tree here that it will set up the directory within your system under Niagara, and then scrolling down to your actual location. So if we just drop down sys home, you'll see exactly where the Sedona bundles are located within the appropriate version, and then from there your framework, and all the way down into your Sedona network where your kits, manifest, and platforms are located. Now the kits, manifest, and platforms we made available to any of our authorized resellers via your provider, your local distributor, or OEM. The generic platforms, kits, and manifest are bundled up in the Sedona TXS framework. Okay, well, once we've installed that, now it's time to get started with your actual version. So we'll open up the config and then drop down drivers, and you'll see we have no Sedona Gen 6 LP network at this time, so we need to install it. So you simply open up your control palette, and in this case I already have them here, but to show you from scratch, we're going to open up the palette and we're going to search for Gen 6 LP. So you scroll down until you find the Gen 6 LP network, open it up, and you'll see from there you have your Sedona Gen 6 LP network. You simply drag the network from the palette onto your drivers folder, select OK, and your Sedona network is now in place. The next thing we need to do is look for the in Sedona jar file, and what this will do is will give you the SOX tunneling service. And of course, as you know, you can either scroll or just search for in Sedona here, locate, and then take the SOX tunnel service and drop it in the services folder. Now immediately upon dropping the SOX tunnel service in, go ahead and open it, and you want to make the authenticate with user service false. This will expedite the process of the tunnel feature, which you'll see momentarily. So that needs to be step one. Now it's time to set up the Sedona network. To give us a little more room, let's go ahead and close the control palette. So go into the property sheet of the Sedona network, and good rule of thumb is to start from the bottom and move upwards. So what we're going to do is start from the address map, which would be step one. You can see it has a generic 192.168.1.0 network. We typically utilize a 10.10.0 network. Now the key is to make the final octet .0 for it to function properly. If we were to start with a generic mid-range number and try to save it, it's going to give you an error that the last octet must be 0. So simply start with the appropriate addressing scheme and hit save or continue making your changes. Now we've set the base IPv4 address, and this is what's going to map your IPv6 or 6LoWPAN address from your Sedona wireless devices to the IPv4 network within Niagara. All right, the next step would be to select the channel. You can see here that channels available are 11 through 26. There are 3 channels that operate outside of any standard 2.4 gigahertz 802.11 or .15.4 frequency, and that's channels 18, 25, and 26. So I typically utilize channel 26. The next would be to select your PAN ID. This is your unique identifier for your network. Any devices you're going to communicate from your Jace have to be on the same PAN ID. So in this case, we're going to set ours to 0, and it can be any hexadecimal combination. As you can see, default is DEFA. All right, we've made those changes. Next, we're going to enable Show PAN Server. By enabling this, it gives you the feature of the service PAN, which you will see momentarily. So we've made these changes. We've started with your address map and set up your 10.10.0 network, selected appropriate channel and PAN ID, and now we've enabled Show PAN Server. The next thing to do is enable our Sedona network. So we've made that network enabled. We've selected true and saved. So the next step is going to be to actually look for devices that we're getting ready to power on. So we're going to start with a few devices. At the same time, I'm going to open up a separate window so we can see the Sedona network as we, let me go back to the property sheet quickly so we can start watching the address map here. Now, as devices populate, we'll see, as you see right here, 2 devices just joined the network. Now, this is your RF side of the network. This is where you will go to do any type of troubleshooting if you have RF issues. This is indicative of the GENIC network. And you'll see here we have the 6LoWPAN address mapped to the IPv4 address, which is different from the Sedona network. As you can see, no devices are here yet. In troubleshooting a network, if you have problem with Sedona devices and you're not sure if it's the Sedona network giving you issues or the wireless, this is where you would go back and look and see if the devices are online. OK obviously means they're online and communicating. If they're offline, you'll have a negative or a dash. So let's go to Sedona network and go ahead and discover. So you simply click the discover function, and now the Jace has gone out and it's found these 2 devices. So you can see IP addresses 1 and 2, which match the 2 that popped into the GENIC network. You simply add the 2 devices to your network. All right, so now we've added 2 unknown devices to our Sedona network. You can see immediately they have populated within the network here. Now we need to identify which device is which. So what we're going to do is look for the WIO24, which is our first device, by hitting the service pin. So once we hit the service pin on the 24I/0 controller, one of the devices, as you see here, will highlight purple. You simply can right-click at that point and name the device, and we're just going to call it Aurora WIO24. So now let's hit the service pin on the WIO12, which will be the second device. There you go. And rename it. So WIO12. All right, so now we have the 2 devices. Let's move the screen up just a tad, and we'll initiate the next sequence, which is going to be the tunneling. This is where you actually do your local programming of your controllers. So before we bring on any additional devices, we're going to do some tunneling. So let's right-click on your controller here, and you'll see the Open SOX Tunnel session. If you had not dropped in the SOX Tunnel service, this would not be available to you. Now you can enter into a SOX Tunnel session from this location or from your tree by doing the same thing. So you've got Open SOX in both locations. So from here, we'll just open the session. The generic username and password is admin, no password. So we hit OK. And immediately you can see we've identified the device. We're now inside the controller. So here's the Sedona network up here. We've now opened up a SOX connection with the actual controller. So let's go and see what's going on within the device itself. So dropping down the app menu, you can see we have the program folder. So double clicking on the program folder, we'll see what actual program is running in the device right now. And you can see we're running a demo station or a demo control sequence on the device, and data is coming in the AIs. Right now we're reading ohms and sending out through a reset button to an analog output to run a LED display. So to show you how easy it is to manipulate the control feature, you would go to your window and open up your Sedona palette. Now the Sedona palette is only active while you're inside of a controller. And you can see we actually have features here. So if we drop down the menu, we can see all of the kits that are associated with this particular controller that we've enabled. So if we wanted to drop in an additional Type 3 thermistor AI, you simply select the AI 3T and drag over the 3T, and now we have a Type 3 thermistor into our network. At that point, you can select, rename, select the AI number on the device. As you know, there's 1 through 8, so you could select the device for the 8 universal inputs. All right, so let's back up, and you can see now that because we've added something to this program, the app has an orange star. At this point, I would need to right-click and save the application if I wanted to keep this. So let's save it for the time being, and I've made the changes, but we want to keep it, so we'll do a restart on the device, which is imperative once you make a change. So we're going to restart the device, hit yes. The device fell offline. If we go back to our Sedona network immediately, you see it drop off. It should come back relatively quickly. And this again is where you can go back and forth from your network here and watch the RF. So we saw it go yellow in the Sedona network. It's back okay there. So if we come back here, he's back healthy. So we can enter into this SOX tunnel session again and go into the program. All right, what we're going to demonstrate next, as soon as it loads, is how to change the application. You can see now the analog value that I added is still there. It took the program change. But let's say we have previously built a unique profile or air handling unit application that we wanted to utilize over and over again on a job. So instead of having to build logic independently of each controller, you can place pre-configured apps in the devices themselves. So by utilizing the app manager, we can do a get and a put. So if we've built the app we just looked at and we want to get it, you simply lost connection. Reconnect here. Go back into my app manager. We can do a get, and this is where you can actually get the application that you previously loaded. So, and you can name it something particular to your demonstration or your application. So in this case, let's call it webinar change 3, pan 0, because that's the pan ID, just because we frequently make changes on the pan IDs from network to network. It's always good to keep that in the name, that way you know. So now we've uploaded and got the application, but we want to put a different one in now that is specific to the job. So let's go into, we'll browse into previously built applications, and we're going to put the WIO24 show pan 0 application, which is a SAX file, into the device. We hit next. It goes through and it looks for all the kits that are located in this device. Now there's no dependencies that aren't previously selected, otherwise you would have errors here that you would simply correct by selecting the appropriate kit. But because everything appears to be fine, we can simply select next and finish, and it will rebuild the application, commit the files, and then it will give you the option to restart. So now we've already reprogrammed the controller. We simply hit restart. Now once again, you'll see the device drop and come back online. All right, device is offline, so we can watch here. Okay, he's back online. So instead of going there, we know we can just double click because we know which device we're in. So now let's go to the program, close this again, and let's see what we have. All right, and there's the new program. So it's that easy. You simply place the application in, and you can see now we're monitoring inputs from multiple different AIs at this point, and sending that data through different outputs. Again, this is a unique and generic application for a demo. So it's that easy to place the applications and change in the devices. Now, under the service tab in the device itself is where you'll have your platform and users. Now, the user tab is where you can provide unique user identification for login to the device itself. Under the platform is where you can change the PAN ID. So if you had multiple JACEs on one job and you needed to take this device through its location and send it to another JACE, you could change the PAN ID and immediately it would join the network with the associated PAN ID. And then it would obviously map a new IPv4 address. Now, the min beacon LQI is a feature we added to Tritium to force the network. By default, the RF devices look for the shortest route back to the coordinator or the JACE. That's not always good in a control sequence because you want a very strong signal. So by being able to adjust the min beacon LQI, you're able to dictate the minimum link that a device must have to communicate back to the coordinator. So typically we'll make this 100 to 120 to give a higher threshold and more room for error on the lower side. So if it connects to a device, it has to have a starting link of 100, and then it can drop down to 70 without a disconnect. So very important feature here as you build networks to know that you can adjust that on a scale of 0 to 255. 70 being the absolute minimum we would ever want to see, but again, anything 100 or better is what we start with. Okay, so that's your min beacon LQI in the platform setting. So let's go ahead and disconnect from this guy. And I want to, we don't want to save anything. Let's go back to our Sedona network. I want to demonstrate one quick feature in a SOX tunnel session with the 12IO device. If I were to drop down in the tool section and go to the app manager and I wanted to put an application, and we're going to put an app that we built for a 24 into the 12 or start the process. If we select that same application and hit open next, this is where you'll see the dependency issue. Because this is a 12, it needs the actual devices that we've placed into the 24 to be added to the 12. So this is where you would go through. So if I wanted to complete this process, I'd simply scroll down into the kits to find the dependencies. So if this is looking for the AI ohm for the 8646, if I select it, it removes it from the dependency. Now I'm not going to do this because this will take a little bit more time. I wanted to show you how easy it is to start selecting these things, and as soon as you do that, it removes your errors. All right, let's cancel that, but let's show you where the actual kits are located within the device. We'll disconnect from this guy and go back into this device itself. And once you're there into the controller, you can go into the kit manager for each device. This is where you can reduce the overhead by removing things from the controller you're not going to need, or by adding the devices or kits that you could utilize or need to utilize. In this case, you can see all the kits that are available from download from our website that can be placed in the controller to provide you with the ability to build your custom logic. One thing that was added in the new devices in 5148 modules, which are installed on the 12 and the 24, is now you're able to utilize the full control kit because the memory has increased by over 500%. So literally there is no limitation in building custom logic in these devices. All logic does reside in the device itself, so it is a programmable device that does not require dependency on the JACE for communication, just to run the control sequence. All right, so we've covered the basics of setting up a network and how to tunnel. Let's bring on some more devices so you can see how additional devices join the network. All right, let's go back to the property sheet. And as we power on the next batch, we're going to go ahead and power on 10 devices. And what you'll see as we bring the devices online, they'll start joining. And as they join, the IPv6 address will be mapped immediately to an IPv4. All right, there's your next 5. And if we drop down, we should have a total of 12 addresses. There they are, so the 2 originals and the 10 new. So if we go back to the Sedona network, let's go ahead and discover the new devices. So that quick, devices 3 through 12 have joined the network. We simply add them, hit OK. And at this point, we'd go through the service pin feature again if we needed to identify. In this case, for time's sake, we're going to assume we've done that, rename, and this is where you can start specifying your devices. Rooftop unit controller 1, AHU 4, an example, lighting panel 2, and so forth. And now you're building your network. So in that case, this is how the process begins. So let's go ahead and bring on the remaining 6 devices. We'll go ahead and power that on so I can show you the remaining features before we move into some product specifics. Okay, more devices are joining. We should have one more. This last entry, which will be 18, should be our bullet that I'll demonstrate when we discover points. Okay, there's all 18. So let's go back to our Sedona network and let's go ahead and discover anything new. Scroll down, there's devices 13 through 18. So a relatively quick process. We add to the network, and instead of naming all of them, let's just go ahead and rename 18 bullet so we can see what's going on. So we have the devices. Now, the next step is to actually tell the Jace and the network that these are all routers. By default, they come in as an unknown device. So by simply double-clicking or right-clicking and going to the property sheet, you'll see the device type is unknown. So we need to quickly make each device a router. And I'll stop midway and show you why. We'll name the first 4 and then take a break and show you the reason to do this. All right, we've got the routers named for the first 4 devices. One of the biggest features that we like in the Gen 6 LP network is the pan sheet, and this is a very valuable tool for troubleshooting your network as well. So if you go into the Views category and select pan sheet, what this does, it at a glance gives you your network. And you can see we've got a few devices named, and all the rest of them, because we haven't named them, they have no idea what they are, so they haven't joined and shown the appropriate route. So let's close this out, go back to our Sedona network. We left off with 4, and let's just continue naming these devices. No, let me go back. Yeah, I need to save that. It told on me. So we're going to save these devices, and as we're doing this, I'll continue to explain a few features. In the pan sheet, obviously now that we're naming them routers, this just gives the network a better understanding and how to document the pan information. Now, pan information is the pan info. That is your connection to and from parents or children. Very important, because as networks grow, it's important to know the routes that the devices are taking. Now, the difference in a true mesh and a tree network, which is what we utilize, is that a mesh network, a true mesh under Zigbee protocol, has a limit of about 120 devices. In a tree network, using which is what, again, we utilize, you're not limited to the 120. You're upwards of 500 devices. So what you're able to do in a star or tree, a tree network, is create a network where all the devices still repeat through each other, but to do so, they're not listening for every other device as in a true mesh, which is better for a controlled environment because you don't want excess overhead. All right, we've named the devices all routers. So if we go back into the property sheet here, instead of going down, and you can see here you have the pan info polar. This is where you can set the frequency, how often the front end or the Jace goes out and looks for the pan information. We're going to speed the process up and just delete all existing pan info, because previously when I called for it with the pan sheet, we were missing data because we had unidentified devices. So we've deleted all pan info. Now we want to load all pan info. So if we go back now and go back to the pan sheet, we should see a better visualization of our network. And wow, all the devices are there. And you can see how they've connected. In this case, because of how we power the devices on, we have 3 direct children to the Jace, and each of those children have a set number of devices. But in this case, because it's a controlled environment, if we wanted to remove this controller from the network and force these devices to connect directly to the coordinator, we could actually reset the 12IO, reboot him, and force these guys to find a different route. Now, depending upon the connection timing, this would potentially cause these devices to join the 24 or simply go back to the coordinator. So again, this is how you can manage the network, but you can see at a glance by selecting the coordinator very strong links. If you simply place your mouse in the white area of the screen, you will get all of the connections between the devices, and nothing's yellow. You can go from each one to look at the different connections between devices and verify what's going on. Now you have NA here. Now that's very important. That means that the pan info polling was missed. So you simply go back into your pan sheet or property sheet, delete and reload the pan info. So, but again, this is how you can manage your network more effectively to troubleshoot if you're having issues. So in a controlled network, this is a very valuable tool, especially when you get up to 100 or so devices on a network, as we've done before, being able to identify where your weak links are, if any. All right, so back to the Sedona network as a brief recap. We've dealt with how to set up your Sedona network, how to utilize the address map for your wireless troubleshooting, setting up your PAN ID and your channel, enabling show PAN for your service PIN, and then enabling your network. Again, you can utilize any of these features to change settings if you're seeing some devices that potentially may be receiving or causing interference by simply changing the network parameters with your channel. You could potentially eliminate that. Again, because it's such a wide frequency at 2.4, your interference levels will be very minimal. All right, so that's the basic setup. Now let's go into some product specifics so you can understand what devices we're actually talking about. So we discussed the 24IO controller. This device has 8 universal inputs for resistance, voltage, and current. 4 dedicated digital inputs for contact closure, pulse counting, 6 relay-driven outputs, and 6 analog outputs. Has a built-in EEPROM, real-time clock, and backup battery. That is just to keep any program logic that is based off of clocks live in the case of communication loss where it cannot synchronize the timing, or in the case of a loss of power to the device, the real-time clock will maintain its setting until power is restored to the controller. But because obviously the logic resides in the devices, constant communication with the front end is not mandated. The next device is the WIO12, a smaller version of the 24 with 4 universal inputs, 2 dedicated digital inputs, 4 relay-driven outputs, and 2 analog outputs. The 4IO, this device is made with 1 of each type of input for very small controls applications. Same features as the 12 and 24, just with a reduced IO. The 40i module, again, 4 dedicated digital inputs. This device we've utilized on numerous applications, including some government projects for water, gas, and kW metering. This device also has an EEPROM, real-time clock, and backup battery, so we can count the pulse inputs, store the device, and let the JACE request information on schedule, so we can obviously keep the network healthy. A 40O device, again, it's relay-driven outputs. Logic, again, can reside in the device if need be, or it can be used as basically a wireless-driven remote wireless relay. 4UI, 4 universal inputs for resistance, voltage, and current for just strictly monitoring applications, monitoring status, runtime, tying in CTs that have a voltage input. So very, very useful device in a lot of monitoring projects. The WIO4 and 6WP, the difference in the 4 and the 6 is the 6 comes with 2 analog outputs for driving lighting circuits with dimming ballast. The 4WP strictly has the 2 UIs and 2 DOs, relay driven. This image is an older snapshot of our device because there's a high voltage power supply section in the middle of this one. The first device was made to take incoming power from 120 to 277 and or low voltage input at 24 volts AC or DC. We've now reverted back to strictly 24 volts AC or DC incoming power. The UIs, as you can see here, are all dip switch selectable to go back and forth from resistance or voltage inputs. The enclosure, which makes it the WP model, is a NEMA 4 enclosure. So we've utilized this in a lot of industrial applications where dust or debris is an issue, and in exterior lighting applications or metering projects where they snap to the box on the side of a lighting panel or a breaker box. The Bullet, basic utility light intelligent transceiver. This device is probably our highest seller, utilized to simply replace a standard NEMA twist lock photoreceptacle. This device has an onboard current transducer which provides true RMS voltage monitoring and current monitoring, which then gives you the calculation for exact wattage. So by utilizing our device, an end user now knows the exact energy consumption of each street light. Because the device also has a real-time clock, EEPROM, and backup solid-state battery that is an energy harvesting device, this device now becomes a standalone controller, not requiring communication from the JACE. So you could technically deploy this system across a college campus, a municipality, hospital, mall, what have you, and lose communication from the JACE, and the devices will run on the last known schedule that has been uploaded on a weekly or bi-weekly basis based on sunrise, sunset, and or Julian calendar scheduling. The only offset that would have to be accounted for is midday storm override or an event that would call lighting to come on in daytime hours. And for that, we use photocell arrays around the network that communicate back to the JACE. And that would require communication from the JACE to the network. Now, we have had multiple applications for this product. Two of our latest installations, which encompassed more than 300 or so deployed, provided ROIs for the customers in less than 1.6 years. So it's a very big energy saving device with an extreme low cost and return on investment just by utilizing some advanced scheduling. And consider 100 parking lot lights, each with 1,000-watt bulbs, all coming on at one time is 100,000 watts of inrush. Well, with control logic, obviously being able to bring the lights on in groups of 5 or 10 and providing offsets to give you the ability to not turn the lights on when a standard photocell or time clock would by getting a 10-minute offset in the morning and 10-minute offset in the evening, just simply reduces energy. Parking lot applications where you're able to turn off one of a 2 or 4 bank lighting circuit and leave just enough light for security. Another big feature that we've utilized. Again, it's all about returning the investment for the devices and then a total energy reduction. So very popular and high volume selling device. Kind of give you an idea of how network's set up. Again, this is just a very crude graphic, but it shows the JACE in the middle communicating to wireless devices, whether they're set up for rooftop units, air handling units, metering applications, or the lighting. You now have one system that can communicate to multiple controls networks. So JACE goes out and communicates to devices, and you can see in this case we have 4 direct children to the JACE. Each of the children are responsible for 1 to 10 devices. Each coordinator and or device can communicate to up to 10 children. So the JACE can have 10, each of the 10 children of the JACE can have 10, and it keeps going down. So you can create a very broad and deep network. So in this case, if communication loss takes place or power failure on one of the devices, the network simply switches and finds another route. So as you can see from the previous screen, we had 4 children, we lost 1, so the child at the top middle is now communicating to the majority of the page, and now the other 2 devices have maintained their connection. And then as networks change, again, now we have 5 children and the device is maintaining communication on the network. So very strong network. They function very well in maintaining the self-healing portion of the network. So there's no concern for having to maintain direct line of sight. They operate in a pseudo mesh environment, as explained earlier, that is self-healing. The advantage of this type of system is if it is a vast network, you're able to deploy devices set up as repeaters with no logic just to pass the RF data. To give you an idea of range, there's applications we have where we're sending single devices in excess of a quarter mile back to the front end Jace with higher gain antennas. One of our government applications, we're covering more than 2.5 square miles with one Jace and over 60 devices. So you can see the usefulness, especially in metering and outdoor applications. In building applications, we've seen projects where the Jace from the bottom floor is communicated to air handling units through 2.5 floors of concrete and steel directly to the Jace. In those type of projects, depending upon the link quality, is where you may want to adjust your min beacon LQI to force it to have a stronger signal. But the power to penetrate through walls and floors has been very, very positive. All right, the last thing we want to show, and then we'll close the presentation, is the location to obtain the needed manifest kits and platforms. So your OEM or distributor can provide you access to this information, but we have now a client portal where we will keep updated and obviously publish changes, and this is the admin account. So let me log back out and go in as a guest, and this would be the view that our customers would see. So you have the ability to look at your files where you can see Sedona 1.1 manifest, and so if you're working on a project that has the 8646 or the 24IO controller and the 12 and then your 4UI, you can download just the manifest that you need, as well as the standard manifest that accompany what is automatically loaded in your Sedona framework. Provided a link for the bundles as a zip file, and then additional documentation that we will publish, your platforms, and then applications. This is a new folder we've provided and given some users the ability to upload files. So as your provider builds custom applications that can be shared through the community, we will allow approved applications to be published for download. So when custom applications for air handling or rooftop unit control or even lighting applications are built, we will make them available to our customer base.